Welcome to this video. In this video, I will be talking about conic programming. And conic programming, I will particularly be introducing primal and dual problems, what are cones, what are dual cones, and these things. And the primary idea is that conic programming is very useful because a subclass of conic programming called semi-definite programs that I have written here. So a subclass of conic programming called semi-definite programs find a lot of usefulness in quantum information theory, particularly a lot of entropic quantities like mean conditional entropy, max entropy. Further, a lot of measures of resources like entanglement, then coherence. These can be analyzed by using semi-definite program. Particularly, there is some specific kind of quantities that I have highlighted here. So these are two we will discuss, and we will also talk about robustness and how you can frame the semi-definite program of robustness. Further, conic programming helps in applying tools from convex analysis to quantum information theory and in various applications of mathematics in general. What is important to think is conic programs are kind of a toolbox. So they are like a toolbox using which you can convert one type of problem. So you have some problem which is an optimization problem. Optimization. So you have some optimization problem and you convert a seemingly complicated optimization problem into a different kind of optimization problem. So this will be called as primal problem, and you convert it to something called as a dual problem, which we will discuss how to convert. So these problems are very much linked with each other and both are optimization problem. So with this brief idea, we start conic programming. So these semi-definite programs, I must also say that they are such that they can be solved with reasonable efficiency and precision. So you can be precise. So efficiency and precision on classical computers. So you can classically solve these problems. So with this little motivation, we start the idea of conic program. So the first important ingredient is what is a convex cone. So we have convex cone. So a convex cone is basically a convex set in the sense that probabilistic mixtures of elements belong in the set, and it is a cone. And what it means for it to be a cone is that it is, I denoted by K, it is a subset of some vector space V, some vector space, such that for all u that belongs to K, if you scale it by a positive number, lambda u belongs to K, where lambda is greater than equal to 0. So if you scale the elements by a positive number, they still lie in the cone. That is what it means. I mean, they still lie in the set. So this is the convex cone, and given this, there is the idea of the second idea, which is a dual cone. So let me write it down. So you have dual cone. So for understanding dual cone, we first say something about what is the dual to a vector space. So given a vector space B, we have a dual space V star, and this V star contains all the functionals that map V to the real number. So here the underlying field I am taking to be real because that is what we will be needing in the entire discussion. So this dual that we have, it can be associated with the idea of inner product. So suppose A belongs to the dual, then the action of A on a vector x, so x belongs to V, the action of A on a vector x, this entire thing belongs to R. So this can be said to be as an inner product. In this way, you can associate A with an element A tilde that belongs to V. So this means that there is some kind of an association with the states which are in the dual with the states in the actual vector space. So this association I will be using sometimes, and this is kind of associating a vector V with a bra vector V that we know in standard quantum mechanics. Now with this idea of dual space, we talk about what is a dual cone. So what is a dual cone? So a dual cone is denoted by k star, and this is equal to the set of all vectors v belonging to the dual space such that the the inner product of v with u is greater than equal to 0 for all u belonging to k. So this is the dual cone to any set. So here you can put any set here. We will be interested only with convex cones. So I write here this is a convex cone. But instead of convex cone, it can be any set. So further, one important idea is that the dual, if you do the dual two times, this is again k if k is a closed convex cone. So this is something that one can show. I will not go into details of this. With this we will discuss one example, and the example that is most useful is the following. So the example is that of if I take the vector space to be set of Hermitian matrices over the real numbers, they form a vector space, and then I take the convex cone to be a set of positive semi-definite matrices. So they form a convex cone because they form a convex set, as well as you can scale any element by a positive number and it's still a positive semi-definite operator. So this set, as you can see, is very useful in quantum information theory because the set of density matrices are contained in this set, which has just trace equal to 1. They are trace normalized. Now with this idea we talk about what is the dual of this. So what is dual of POS, which is defined as K. So what is the dual of positive semi-definite matrices set? The answer is, so this is kind of a theorem. It says that the dual K star is also positive semi-definite operators. So this will be useful in several times, particularly when we frame the semi-definite programming, that the dual of the set of positive semi-definite matrices is the set positive semi-definite matrix. And the way to prove it is we take an element, suppose W, and we say that W belongs to K star, then this implies W belongs to POS, which is also K, and likewise we say W belongs to POS implies W belongs to K star. So here POS is the K set. So let's prove the first side. So if W belongs to K star, this means that psi W psi is equal to trace of W times psi psi is greater than equal to 0 because particularly because W is belonging to K star. And what is K star? Let's remind ourselves. So K star is the set of all vectors V such that V W is greater than equal to 0 for W greater than equal to 0. Now I am using this thing here. So what I am saying is I pick a W state, and for any V, so this is replaced by the trace, the Hilbert-Schmidt norm, the Hilbert-Schmidt inner product. So it is trace VW, and here this is the inner product that I have written here, and this is greater than equal to 0. So this means W belongs to POS, which is equal to K, which is defined as K in our example. And on the other hand, if W belongs to POS, then we have to show that it belongs to K star, and that is also simple because we have to just show that trace of WA for all A greater than equal to 0 is greater than equal to 0, but trace of WA is summation over I lambda I WI. And here I have used the spectral decomposition of A, where A is a positive semi-definite operator, and this means that these lambdas are positive, greater than equal to 0 by definition, and this factor is also positive. So this factor is always also greater than equal to 0, because I am starting with the assumption that the W is a positive semi-definite operator. So this means trace WA is greater than equal to 0. So let's write it down. So trace WA is greater than equal to 0 for all A belonging to positive semi-definite operators. If W belongs to positive semi-definite operator, so this means W also belongs to the dual space, the K star space. So this means that both the spaces are contained in each other, and hence the dual POS dual is POS. So with this I stop this video. I am going to divide this discussion into small sections. In the next video I will talk about the primal and the dual problem.